The confidence interval is given by the following equation: x bar plus or minus z times sigma over the square root of n. The x bar is going to represent the center of our interval, and the number to the right of the plus or minus represents our margin of error. X bar is also known as the point estimate, the center of our interval, and the margin of error is the z times sigma over the square root of n part of our equation. This is also known as the maximum error. The sigma over the square root of n is also known as the standard error. Typically, for level of confidence, we usually use 90%, 95%, or 99% level of confidence. You will never see us using 100% level of confidence because 100% confidence doesn't tell us much. I am 100% confident that all of the students in my class are from age 0 to infinity. That doesn't tell me much. So in general, we usually use 90, 95, or 99% confidence. Students' t-distribution. It is unlikely that we know the standard deviation of the population and not know the population mean. So instead of using sigma, we're going to actually use S, which represents the standard deviation of the sample. Now, according to our central limit theorem, Z is not equal to this with the S in the formula. The central limit theorem states that Z is equal to x bar minus mu over sigma. Notice this is sigma and not S from the central limit theorem. Now, instead of calling this Z, we're going to call it T. So we have a T distribution now that is equivalent to x bar minus mu divided by S over the square root of n. Again, notice that this is S and not sigma. So we're using this in place of the population standard deviation because it's very difficult to know what that is, but it's easy to calculate the sample standard deviation. So T is essentially an estimator for Z. Now the T distribution has several characteristics, just like Z. 1, it is continuous. 2, it is bell-shaped and symmetrical, just like Z. 3, there's more area in the tails of the distribution than Z. That is because of the extra variability because of the varying sample sizes. 4, the T distribution changes shape according to their degrees of freedom. And the degrees of freedom is calculated by the sample size minus 1. As the sample size increases, the T distribution approaches the Z distribution. Remember, the T distribution is an approximation for the Z distribution. Now in this graph, you will notice that for the normal distribution in blue, we have the bell shape that we're used to. The T distribution in red, here in the center, has a wider tail on either side of the distribution, but if n increases, it gets closer and closer to the z distribution. We have several different cases. Case 1. If the degrees of freedom is greater than 1000, then we're going to use the formula with z in it. The reason we use this formula with z is it's really close to z since n is so large. If the degrees of freedom is less than or equal to 1000, we're going to use the formula with the t in it because it's not close enough to z, so we'd rather use t. When using technology, make sure you use t. Let's try our first example. The NCAA reports that the mean number of hours spent per week coaching and recruiting by assistant football coaches is 70. A random sample of 50 assistant coaches showed the mean to be 67.86 hours with a standard deviation of 8.2 hours. Construct a 99% confidence interval for the population mean. Does your interval support the claim made by the NCAA, or does it cast doubt? Why? So in this problem, I need to locate the sample mean, which is here, 67.86, the standard deviation, which is 8.2, and I want to calculate a 99% confidence interval. Now to calculate the confidence interval, we need to determine which column to use. I need to use the formula 1 minus the level of confidence divided by 2 to calculate the column I need. Now 1 minus 0.99 divided by 2 is equivalent to 0.05. So that's the column we're going to use for our t table. Now the degrees of freedom in this case is n minus 1, so we have a sample of 50 assistant coaches, so we know the degrees of freedom is 49. And we're going to use row 50 because our t-table does not have a row 49. 50 is the closest one. 0.05 and row 50. This gives me a critical value of 2.678. Now in the problem we have the sample mean is 67.86. The critical value from the t-table was 2.678. The sample standard deviation is 8.2 and the sample size is 50. So we're going to plug in everything into the formula. And I have 67.86 plus or minus 2.678 times 8.2 divided by the square root of 50. Now when you're doing this, always calculate the right side with the calculator first. And that gives us 67.86 plus or minus 3.106. Now in order to do this problem on a calculator, I always do the subtraction first, then I'll do the addition separately on my calculator. So 67.86 minus 3.106 gives me 64.754. Then we'll also do the addition and with the addition we get 70.966. This is our confidence interval. The lower bound is on the left and the upper bound is on the right. We are 99% confident that the average time spent recruiting and coaching by football coaches is between 64.754 and 70.966 hours per week. Yes, my interval supports the claim since 70 is in the interval. Now, if you look at the t-chart, the last row of the t-chart contains z, because as t approaches infinity, the t distribution approaches the z distribution. A hospital administrator wants to estimate the mean length of stay for all inpatients using that hospital. A sample of 1,049 records of patients yielded a mean stay of 7.4 days and a standard deviation of 3.7 days. Construct a 95% confidence interval for the mean length of stay for all inpatients at this hospital. Again, we have to calculate our degrees of freedom, and that is n-1, which is 1,048, because our sample size was 1,049. Since the degrees of freedom is greater than 1,000, we have to use this formula, the one that contains the z, because our t distribution is so close to z, we'll just use z. Now, to find the column, we use the same formula, 1 minus the level of confidence divided by 2. In this case, we have a 95% confidence interval. And we're going to use the column 0.025 for our column. The row, since the degrees of freedom is greater than 1,000, we're going to use row Z. The column 0.025, and the last row gives us a critical value of 1.960. E is 1.96, X bar is 7.4, S is 3.7, and the sample size is 1,049. Plugging in everything into the formula, we have 7.4 plus or minus 1.96 times 3.7 over the square root of 1,049. Now when I do the calculations, I want to make sure to simplify the right side of the plus or minus first. And that reduces to 0.22. When I do this on a calculator, make sure to subtract first and then add. So 7.4 minus 0.22 gives us 7.18. And doing the addition yields 7.62. So our confidence interval is 7.18 to 7.62, and thus we are 95% confident that the mean length of stay for all inpatients at this hospital is between 7.18 and 7.62 days. Now we're going to try part B, which is to construct a 99% confidence interval for the mean length of stay for all inpatients at this hospital. So instead of 95%, we're doing a 99% confidence interval. So again, we're going to calculate the column, which is 1 minus the level of confidence divided by 2. And this is going to be the column we're going to use, 0.005. The rho is rho z again, since the degrees of freedom is greater than 1,000. So the column 0.025, and we're going to go to the last row. And our z value is 2.576. The sample mean is 7.4. The z is 2.576. The sample standard deviation is 3.7. And the sample size is 1,049. We'll plug it into the formula to get 7.4 plus or minus 2.576 times 3.7 divided by the square root of 1,049. I should simplify the right side first on a calculator, and this gives me 0.29. So we have our confidence interval of 7.4 minus 0.29 first to yield the left endpoint, which is 7.11. And then I'm going to do 7.4 plus 0.29 to give us the right endpoint, 7.69. Thus, we are 99% confident that the mean length of stay for all inpatients at this hospital is between 7.11 and 7.69 days. Note, in the formula, we can control two things. We can control z, the desired level of confidence, and we can control n, the sample size. Now, z influences the margin of error. The higher the level of confidence, the wider the margin of error. The n is in the denominator, so as the sample size increases, we're dividing by a larger number, so the margin of error also decreases. If the sample size is small, then our margin of error gets larger.